Welcome back. In this section, we shall state two theorems about space curves that have the same flavor as those of the preceding sections. Theorem: Isoperimetric inequality. Let alpha be a simple closed regular plane curve of length or perimeter L. Let A be the area of the region bounded by alpha. Then L square greater than or equal to 4 pi A with equality if and only if alpha is a circle. Thus, of all curves of fixed length L, the circle bounded the greatest area. Proof: let L1, L2 be two parallel lines tangent to alpha with alpha bounded between them. Let beta be a circle tangent to L1 and L2 which does not intersect alpha, and let R be its radius. Choose coordinates x and y for the plane with the origin at the center of the circle with the y-axis parallel to L1. Let L1 the tangent to alpha at A is equal to alpha of 0 and L2 at C is equal to alpha of S2. See figure 1. The key idea of the proof is to compare the area of the region bounded by alpha with the area of the circle of radius r. Since both the length and the area enclosed by alpha are independent of parametrization, we may assume alpha is a unit speed curve. Alpha may then be written in the xy coordinates as alpha of s is equal to x of s, y of s, where x dash s whole square plus y dash s whole square is equal to 1. The curve beta may be parameterized by beta of s is equal to z of s, w of s, where z of s is equal to x of s, w of s is equal to minus square root of r square minus x square 0 less than or equal to s less than or is equal to s2, root of r square minus x square s2 less than or equal to s less than or equal to L. Equation number 1. Note that S is arc length on alpha but not on beta. In fact, with this parametrization, beta may not be regular, but it is c square. Therefore, the area bounded by alpha is A is equal to integral over alpha x dy, which is equal to integral over 0 to L x y dash ds. Thus, area bounded by beta is pi r square is equal to minus integral over beta y dx, which is equal to minus integral over 0 to L w z dash ds, which is equal to minus integral 0 to L w x dash ds. Thus, a plus pi r square is equal to integral 0 to L x y dash minus w x dash ds less than or equal to integral 0 to L mod x y dash minus w x dash ds, which is less than or equal to integral 0 to L determinant of inner product x dash y dash minus w x ds. The Cauchy-Schwarz inequality together with the fact that alpha is unit speed tell us that determinant inner product x dash y dash minus w x less than or equal to determinant x dash y dash determinant minus w x, which is equal to square root of w square plus x square, which is equal to r. Thus, a plus pi r square less than or equal to integral 0 to L determinant inner product x dash y dash minus w x ds less than or equal to integral 0 to L r ds, which is equal to r L. We have thus shown that a plus pi r square less than or equal to r L. Equation number 2. If we let a is equal to a and b is equal to pi r square and apply equation 2, we obtain root of a pi r square less than or equal to a plus pi r square by 2 less than or equal to r L by 2. Equation number 3, where the second inequality comes from 2. Hence, a pi r square less than or equal to r square L square by 4 or L square greater than or equal to 4 pi a, which is the isoperimetric inequality. Now assume that L square is equal to 4 pi a. We shall show that alpha must be a circle. We first show that x is equal to r y dash. Since L square equal to 4 pi a, inequality 3 becomes an equality. Considering the derivation of 2, we must have equality where the Cauchy-Schwarz inequality was used. Then there is a real number c such that minus wx is equal to c of x dash y dash. Equation number 4. Taking the length of each side of 4 yields square root of w square plus x square is equal to mod c into square root of x dash square plus y dash square, which is equal to mod c. And so 1 implies that c is equal to plus or minus r. On the other hand, 4 also says that c is equal to inner product x dash y dash minus wx, which since the first inequality in the derivation of 2 must also be an inequality is non-negative. Hence, c is equal to r and 4 shows that x is equal to r y dash. A is equal to pi r square implies that r depends on a and not on the choice of L1. Thus, if lines L3 and L4 orthogonal to L1 and L2 are used, circle of radius r is tangent to them. If coordinates x bar and y bar with origin at the center of this circle are used, see figure 2, we would derive x bar is equal to r y bar dash. Since the y axis is parallel and in the direction of the x bar axis and the x axis is parallel to minus y bar and in the direction of there are constants d and e such that x bar is equal to y minus d, y bar is equal to e minus x. Thus, y minus d is equal to x bar, which is equal to r y bar dash, which is equal to minus r x dash. X square plus y minus d whole square is equal to r y dash square plus minus r x dash square, which is equal to r square into x dash square plus y dash square, which is equal to r square. Therefore, alpha is a circle of radius r centered at 0d in the xy coordinate system. Remark: if a closed unit speed curve is noted, then integral 0 to L kappa ds greater than or equal to 4 pi. The 4 vertex theorem. We shall now consider a certain class of convex curves, those with no straight segments or isolated points where k is equal to 0. Definition: an oval is a regular simple closed plane curve with k greater than 0. Definition: a vertex of a regular plane curve is a point where k has a relative maximum or minimum. The concept of a vertex does not depend on the parametrization of a curve. Vertices may be found when k is a function of some arbitrary parameter. Example 1. The non-unit speed curve alpha of t is equal to 2 cos t sin t is an ellipse. It has exactly 4 vertices given by t is equal to 0, pi by 2, pi, 3 pi by 2. L is a line in R2, then there are A, C in R2 with C not equal to 0 such that Z belongs to L if and only if inner product Z minus A, C is equal to 0. Proof: let L be the line given by alpha of t is equal to Z naught plus T V, where 0 not equal to V, which is equal to V1, V2 belongs to R2. Thus, A is equal to Z0 and C is equal to minus V square V1 give the desired result. Theorem 2. 4 vertex theorem. An oval alpha of S has at least 4 vertices. Proof: since alpha is C3, k dash is equal to 0 at each vertex. If k is constant on any segment, then every point on this segment is a vertex and we are finished. We may therefore assume that alpha has no circular arcs, and since k greater than 0, no straight line segments either, and that there are distinct vertices A and B where K takes on its global maximum and minimum. Assume also that A is equal to alpha of 0. We now show that the assumption that these are the only vertices leads to a contradiction. Because vertices come in pairs, this will prove the theorem. Let L be the straight line joining A and B. Since we have assumed that there are exactly two vertices, K dash is positive on one segment of alpha and negative on the other. See figure 2. Lemma 1 says that there are constants A and C not equal to 0 such that Z belongs to L if and only if inner product Z minus A C is equal to 0. Because K greater than 0, alpha must be convex by theorem 2. And so L intersects at alpha exactly the 2 points A and B. Hence, inner product alpha of S minus A C is positive on one segment of alpha and negative on the other. It shows that K dash of S inner product alpha of S minus A C does not change sign on alpha. It is non-positive in figure 2. At some points, K dash of inner product alpha minus A C not equal to 0, and so 0 not equal to integral 0 to L K dash inner product alpha minus A C ds is equal to K inner product alpha minus A C for the limit 0 to L minus integral 0 to L K inner product alpha dash C ds, which is equal to 0 plus integral 0 to L inner product minus KT C ds, which is equal to integral 0 to L inner product N dash C ds, which is equal to inner product NC over the limit 0 to L, which is equal to 0. This contradiction implies there are more than two vertices. Since K dash changes sign at a vertex, the number of vertices must be even. Thus, there are at least 4 vertices. The theorem is false if we omit the hypothesis closed or if we omit the hypothesis simple, as the following example shows. Example 2. Consider the non-simple plane curve given in polar coordinates r phi by r is equal to 1 minus 2 sin phi. In rectangular coordinates, this is the curve beta phi is equal to cos phi minus 2 sin phi cos phi, sin phi minus 2 sin square phi 0. We shall show that beta has only 2 vertices. Since the angle theta between the horizontal and T increases as phi increases, K greater than 0 and hence K is equal to kappa. We compute kappa. Beta dot is equal to minus sin phi minus 2 cos square phi plus 2 sin square phi, cos phi minus 4 sin phi cos phi 0. Beta double dot is equal to minus cos phi plus 8 sin phi cos phi minus sin phi minus 4 cos square phi plus 4 sin square phi 0. Beta dot cross beta double dot is equal to 0 0 9 minus 6 sin phi. Determinant beta dot cross beta double dot is equal to 9 minus 6 sin phi. Determinant beta dot is equal to 5 minus 4 sin phi whole raised to 1 by 2. K is equal to kappa, which is equal to 9 minus 6 sin phi into 5 minus 4 sin phi raised to minus 3 by 2. K dash is equal to K d phi by ds is equal to 24 cos phi minus 12 cos phi sin phi into 5 minus 4 sin phi whole raised to minus 5 by 2 d phi by ds. We see that K dash is equal to 0 only when 24 cos phi minus 12 cos phi sin phi is equal to 12 into 2 minus sin phi cos phi is 0. That is, when cos phi is equal to 0 or phi is equal to pi by 2, 3 pi by 2. Thus, beta has only 2 vertices which are marked A and B in figure 2. Let alpha be an oval and P a point on alpha. Then there is a point P bar where the tangent T is opposite to that at P. That is, T of P bar is equal to minus T of P. The tangent lines at P and P bar are parallel. Also, at no other point of alpha is the tangent line parallel to these two lines. Thus, given a point P on an oval, there is a unique point P bar called the opposite point to P such that the tangents at P and P bar are parallel and distinct. Definition. The width W of S of an oval alpha at alpha of S is the distance between the tangent lines at P is equal to alpha of S and P bar. Definition. An oval has constant width if the width at the P is independent of the choice of P. The next theorem is surprising because it states that the perimeter of an oval of constant width depends only on the width. Theorem 3. If alpha is an oval of constant width W, then the length of alpha is pi W. Proof. Let beta of S denote the opposite point to alpha of S. The curve beta of S is not a unit speed curve unless alpha is a circle. We have beta of S minus alpha of S is equal to V T of S plus W N of S. Equation number 5. Where V is equal to inner product beta minus alpha T and W is equal to inner product beta minus alpha N. Note that the unit tangent to beta of S is minus T of S and the unit normal is minus N of S. Let S bar be arc length along beta so that dB by ds bar is the unit tangent and differentiate equation 5 with respect to S bar. Minus T of S is equal to d beta by ds bar, which is equal to d beta by ds into ds by ds bar, which is equal to ds by ds bar into d of alpha plus Vt plus Wn by ds, which is equal to ds by ds bar of t plus V dash t plus Vt dash plus W dash n plus Wn dash, which is equal to ds by ds bar of t plus V dash t plus Vkn plus W dash n minus Wkt. Comparing the coefficients of t and n, we have minus 1 is equal to ds by ds bar of 1 plus V dash minus Wk and 0 is equal to ds by ds bar of Vk plus W dash, or provided ds by ds bar not equal to 0, 1 plus V dash minus Wk plus ds bar by ds is equal to 0. Equation number 6. And Vk plus W dash is equal to 0. Equation number 7. Since alpha has constant width and k greater than 0, equation 7 implies V is equal to 0. Then equation 6 yields 1 plus ds bar by ds is equal to Wk. Let P is equal to alpha of 0 and P bar is equal to alpha of S1. Then integral 0 to S1, 1 plus ds bar by ds is equal to integral 0 to S1 Wk ds. Integral 0 to S1 ds plus integral S is equal to 0 to S is equal to S1 ds bar is equal to W integral 0 to S1 k ds, which is equal to W integral 0 to S1 d theta by ds into ds, which is equal to W pi. Integral 0 to S1 ds is the arc length of alpha from P to P bar. Integral S is equal to 0 to S is equal to S1 ds bar is the arc length of beta from P bar to P, which is the arc length of alpha from P bar to P. Hence, the length of alpha is integral 0 to S1 ds plus integral S is equal to 0 to S is equal to S1 ds bar, which is equal to W pi. Corollary 1. If alpha is an oval of constant width, the straight line joining P to P bar is orthogonal to the tangents at P and P bar. Proof. In the course of the above proof, we show that V is equal to 0. This fact coupled with equation 5 implies beta is equal to alpha plus Wn, and so the vector from P to P bar is Wn. Now let us conclude the session. In this session, we discussed two important theorems, 4-vertex theorem and isoperimetric inequality. and also explain the concept of oval and its properties. Before moving to the next session, let us try to answer these questions. If alpha of S is an oval, prove that T double dash is parallel to T at least 4 points. Prove that the concept of a vertex does not depend upon the parametrization. Prove that 4-vertex theorem is false if the hypothesis closed is omitted by considering the parabola alpha of t is equal to t square. Hope you enjoy the session. See you next time. Till then, take care.